All right, good morning to everyone, and welcome back to the ACDA online seminar series. We are glad to have you with us this morning, and we're especially glad to have Michael Binder joining us to give our seminar today. Michael is a professor at Stony Brook University, and his research is in the areas of data structures and algorithms, I/O efficient computing, scheduling, parallel computing. If it has to do with hardware and algorithms, Michael seems to be interested. I'm really excited to have him with us today, talking about new bounds for online parallel paging and green paging. And without further ado, I will turn the floor over to you, Michael.
Great. Thank you so much. It's really great to be here. And I have to say, I'm really excited about all of the energetic activity in ACDA. And I think it's a great organization. Let me ask one question before I begin. Can people talk, or like if people have any questions, can they talk, or is that turned off?
As a webinar, I believe they can ask questions by typing them in, which I can read out to you, and we can turn them on individually to talk, but they can't do it without us activating it.
Sounds great. So in general, my preference is to be as interactive as possible, because I always like to have the illusion that I'm talking to actual people. So definitely interrupt, anytime with any question. All right, so this is joint work with Kunal Agarwal and Ratish Das and Bill Kuzmal and Enoch Pesterico and Michele Squisato. As you said, the title is Tight Bounds for Online Parallel Paging and Green Paging. And I'm going to organize the talk by explaining the title. And so first I'll talk about paging, then online paging, and then parallel paging and online parallel paging, and then green paging and online green paging, and finally what I mean by tight bounds. And this is actually a classical problem, 25 years old, at least, I guess, from 1995. And I hope that by the time we come out of the talk, everybody has a sense about how to think about online parallel paging. Okay, so I'm going to begin by explaining what I mean by paging. Okay, so this is a picture showing the classical sequential paging problem. And this is a picture of a computer where we have a processor that is making requests to access pages or blocks. And I'm going to use the word page or block interchangeably. So here we have this processor that's making requests to access pages. And these could be stored in cache, so in a cache of size K, or they could be stored in an external memory that, for the purpose of this problem, we're modeling is as large as necessary. So the pages are either in cache or in external memory. If a page is in cache, then the processor can access it quickly, say in unit time. On the other hand, if the page is in external memory, then it takes S units of time just to bring it into cache, and then an additional 1 unit of time before the processor can access it. And as I said, like the cache has limited size, so up to K pages can be kept in cache at a time. And in the classical paging problem, there's only one algorithmic decision, and that is to control which pages are moved in and out of cache. So since the cache has limited size, if it's full and we want to bring a new page into cache, then we have to eject another page to make room for it. And the objective is to complete this request sequence as fast as possible. And this is the classical paging problem. Okay. The offline version of this problem is well understood and has been for decades. And that's when we know this request sequence ahead of time. And the offline optimal algorithm is to evict the page that will be used farthest in the future. And we've known about this since '66. So this is just evict the page that's farthest in the future, and this is the optimal solution. The online sequential paging problem is when we don't get to see the future. So now we've got these blocker page requests, but we only see them as we go along. But even here, we understand this problem very, very well and have for a long time. So the natural online algorithm is always to evict the page that was least recently used. You always evict the page that was last accessed longest ago. And we have many classical theorems about how well LRU performs. So from an algorithm's, probably the most famous theorem is due to Slater and Tarjan from 1985, where if we have constant resource augmentation, then least recently used, and LRU is constant competitive. That's within a constant factor of optimal. And what I mean by constant resource augmentation is if we run least recently used on a cache of size k, then that's within a factor of 2 of the optimal algorithm with a somewhat smaller cache, say a cache of size k over 2. And so, so this is the classical theorem, which says that if you can't see the future, but your cache is a little bit larger, then that's almost as good as you can do. Okay, and so this is the classical online sequential paging problem. It's very well understood. Now let's talk about parallel paging, which is what this talk is about. So in parallel paging, we don't have just one processor, but we have P processors. And we have P request sequences, and all of these request sequences occur in parallel. And so that's what I've shown on this slightly augmented picture on the right. So now we've got different processors. They access disjoint sets of pages. So the pages in this sequence, the requests for pages in this sequence are different from all the requests in that, are different from all the ones in that, and so forth. So they're disjoint sets of pages. And each processor has its own channel to cache, which means that the processors can access this cache in parallel. That's what I've shown here. And moreover, the processors can move pages between cache and external memory in parallel, and that's what I've shown here. But in the parallel paging problem, we have this restriction that the cache still just has size k, but now this cache of size k has to be shared among all of the processors. So the processors have to decide how to share this single resource, which is a cache of size k. And that's the parallel paging problem. And we've known about, this is a problem that we've wanted to solve at least since 1995. And so this is the common case of in a multi-core system when you have multiple processors and a shared cache. Okay, so this is the parallel paging problem. As I said, any questions, or even if people just want me to repeat something, please put that in the text, or and Blair will transmit it to me because I do like interaction with people. Okay. As before, in the sequential case, there's only one algorithmic decision that we need to make. It's a complicated to describe problem, but there's only one decision to make, which is when a new block is brought into cache, what block should we evict? And so that's what I've shown in this picture. We're bringing this new red block into cache, so we have to evict some other block to make room for it. And the question is which one? And that's the only decision that we're making fundamentally as we run the algorithm. Okay, that's the parallel paging problem. There are, depending on how we want to structure the problem, there are different performance objectives that we could consider optimizing. One of them is makespan, that is the time until every request, the last request is finished, or we could minimize sum of completion times, which would be, the average completion time over all of the request sequences. And there are various other objectives, but these are the main two, and they're distinct but related. Okay.
Michael, we have a question.
Oh, good.
Jacob asks, what if the request sets are not disjoint?
That is a great question. That makes the problem harder, but surprisingly, and that's something that we understand, that it makes the problem a little bit harder, but we don't quite know how much harder it makes it. So I think that's an interesting question about what happens when the requests are not disjoint. Yeah, and that's still an important thing to think about. I feel that it's not as fundamental as thinking about how to share this cache, which is why we focused first on the disjointness. But that is one of the next things that we need to understand in this problem. Make sense? Yeah, so it's a strictly harder problem when there's lots and lots of shared data. I think it's often the case with that there's a little bit of shared information, but most of what the threads are running is distinct, and then we would be able to use all of the reasoning in this talk.
Another audience member has asked whether or not everything is synchronized.
That is a great question, and the answer is no. And we will see this going forward, that it's not fair to synchronize everything. And I will explain in just a couple slides why sort of trying to synchronize it's horrible. You're losing all your performance if you try to synchronize.
Okay, thanks.
Yes, so please keep the questions coming. Okay, so what comes next is I want to explain why parallel paging is really very, very different from sequential paging. And it's a completely different beast. And so in order to do this, I want to talk about some of the unique challenges that occur with online parallel paging that don't occur for the sequential problem. Okay, so that's what I'm going to do now. So the first challenge is how to partition the cache among the threads. And so here we've got processors with different colors, and well, why not just divide the cache evenly among the threads? And this turns out to be a bad idea. In fact, it can be as bad as S, right? This access time S times what would be the optimal solution. And this is as bad as if you didn't have a cache at all. So dividing evenly, you can create situations where this performs very poorly. But even if you have any fixed allocation, where maybe processor 1 has a lot of the cache, 2 has got much less, 3's got a big chunk, and so forth, any fixed allocation is similarly bad. It could be S times optimal, which is as bad as if you didn't have a cache at all. So the issue is that we need to, this is showing is that over time, the fraction of the cache that you want to assign to different processors, this changes dynamically over time. So the challenge is how to dynamically partition the cache among the threads over time, even though you can't see the future. So this is a big challenge, and to me, this is the most important one to think about. But now let's go to the second, which is because we are thinking about how to divide the cache dynamically over time. This also means that we have to think about how to interleave or schedule the individual threads. So this is one of the questions that was asked earlier, which is, do these threads run in lockstep? And the answer is no, because our decisions about how much of the cache we want to assign to each processor cause the processors to move at different speeds. And that's what I've shown here. Maybe processor 1 has done very little, processor 2 has done more, and so forth. And in general, we cannot schedule the threads in lockstep. And that's what I want to show next.
Can I interrupt with another question?
You bet.
Jadong says, in the systems field, a shared cache can be dynamically partitioned by the operating system among parallel threads to address conflict issues. In this way, block replacement would be done by each thread without interference from the others. What do you think about this approach for parallel paging?
Right, so that's a great question. And so let me just echo, which is that one of the things that we can do is somehow partition the cache directly so that each process or processor gets a fraction of cache, and that's set. And then the question is, how do you do replacement? And actually, I'll talk about that in just 1 second. The answer is you can still do LRU. Actually, I'll just say it's in now. So you can still do LRU once you have figured out how you want to partition the cache, and even when the partition changes over time. But the question is, how do we figure out the right way to partition the cache? So once we've figured out how to partition the cache, then the replacement becomes straightforward. And I love these questions. I think a good question is one in which it sort of anticipates by a couple slides what the speaker is about to say. And a lot of these questions have been that way, and the more the better. So the point is that our decisions cause processors to move at different speeds. In general, threads cannot be scheduled in lockstep. So that was one of the other questions. Let me explain why lockstep performs so poorly. So here's an example where with just 4 processors. So the first processor accesses pages between 0 and k over 2. So the working set is like half of the size of cache. The second processor accesses pages k over 2 to k. The third one accesses pages with addresses k to 3k over 2. The fourth from 3k over 2 to 2k. And what this means is that the working sets of 2 of these threads fits in cache, but not for 3. And so not for 4. And what this means is that the optimal algorithm would be to run the first 2 threads to completion, and then run this next 2 threads to completion. And now we're going to have very, very little in the way of page faults because everything fits in cache. Whereas if we run in lockstep, then it's as if the cache is almost entirely useless. So this explains why interleaving is important, but also why lockstep does not work. And which was a question that was, one of the questions from earlier. So the third, this is another one of the questions from earlier, which is, how do we do the replacement policy once we have partitioned the cache? And I sort of vacillated between calling this a challenge and calling this a non-challenge. And I decided an ultimately non-challenge, which is what eviction policy should each processor use? Basically, what are the eviction policies of individual threads, given that the thread's allotment of cache changes over time? And the answer is each processor should still just use LRU. So LRU works within each partition of the cache, but the question is how to do that. Okay, so those are the 3 challenges. And just to summarize, one of them is how to partition this cache among the threads. This is a parallel paging challenge. With sequential paging, there's a single thread that gets all the cache, so it's not a challenge. Then how to interleave or schedule the individual threads. And in sequential paging, there's a total order in which we service the page requests, so that's not an issue. Then this third thing is what are the eviction policies of each individual thread? And I already said that we can just use LRU or a similar type of strategy, just the way we would in sequential paging. So this third is not really a challenge, but the first 2 are. Okay, So this is a summary of what makes parallel paging so fundamentally more difficult than sequential paging. Okay. I mentioned this earlier, that this is a problem that we've wanted to understand since 1995, but I'm repeating it. So this is a problem that's been open for 25 years. There are some results for the offline problem. For example, that this problem is NP hard. So unlike the sequential problem, which is polynomial time, this is NP hard. And even the existing offline algorithms have runtimes that are exponential in the number of processors and the size of cache. And yet we want something that we can run online with a reasonable complexity. And that's what I'll show you. Okay, so this is online parallel paging. And I'm going to give an online parallel paging algorithm that is log P, so log of the number of processors competitive, both for average completion time or makespan. And there's constant resource augmentation. And this is tight. So you cannot do better than a log P times optimal solution because they're lower bounds. And these are results that appeared in recent SOTA and SPAs. Okay. So that's the result. Yeah.
Maurice asks, do stochastic models, which have been published relatively to online parallel paging? I'm a little confused by the wording here. So I'm guessing he's asking about applying stochastic models to this problem.
So that is a great question. And this is so new that I think it's a really, really exciting area to think about, because so many of the questions are interesting and new. And now we actually have, as you'll see, we have a way of thinking about it. And so that's a great question. I don't know, but I'm certainly excited to think about it and excited to talk about it afterwards.
Okay. Thanks.
Because yeah, it's a great question. And as you'll see, yeah, this is a playground for lots of new things to think about. Okay, so now what I want to do is start to give insight. So far I've described the problem, and now we're going to go to the next part of the talk. The way we should view cache is as a scarce resource, which is probably how most of us view cache. So each thread, so cache is a scarce resource, so we want each thread to use as little of the cache as it can. So this is a picture of cache and the threads. I'm not sure why one of them has a magnifying glass, but I thought it was cute, so I'm keeping it. And so what we want to do is to find another problem that explains that cache is a shared resource and models it. And so that's what we're going to do next. And so this motivates a seemingly very different problem, which is the problem of green paging. Okay, so here's the green paging problem. And I don't know if you know if you can see the deep symbolism of changing the banner from blue to green for green paging, but there it is. So now I'm going to describe the green paging problem, where once again, we're back to a single processor. So it's just one processor. And slots in the cache can be powered off to save energy. So, so there's some maximum number of slots, K max, that we can power on. And there's a minimum number that we're required to keep on, which is K min. So we can use all of the cache, K max, or as little as K min of the cache. And then we can ratchet up and down as we see fit. The energy consumption in a time step is the number of cache slots that are turned on. And the objective is to service the request sequence online using the minimal amount of energy. So this is the green paging problem, where there's this new knob where we get to turn how much of the cache we want off, how much of the cache we want on. Okay, so this is the green paging problem. I think I'm going to say the same thing twice, which is, we'll talk about the cache impact, which is just the amount of energy that were consumed, which is the sum over all time steps of the number of cache slots that are powered on. So basically, it's just this picture here. It's the integral over time of the curve of the number of slots that are powered on. And rather than trying to minimize the makespan, or the how long it takes to just complete the sequence, as in classical paging, now we're trying to minimize the energy, regardless of how long it takes. And if we want to minimize cache impact, there's different ways that or strategies we could use for going about doing it. Actually, maybe I'll go this. So here are different strategies. One thing that we could do is we run and say, all right, we'll run in a large amount of time using very little cache and keeping most of the cache turned off. Or maybe we want to turn most of the cache on and try to complete fast. And so the green paging dilemma is, what's the most efficient way of using the minimum amount of cache possible? Okay, so the problem again, given a page request sequence, we want to design a cache space allocation over time and a page replacement policy to minimize the cache impact to service a request sequence. And that's the problem. And for the page replacement policy, it turns out that LRU works just fine. And so it really is a cache space allocation problem. Okay. So now at a high level, the way we are going to solve online parallel paging is starting from online green paging. So we want to solve the green paging problem independently for each one of these threads. And now we're going to get sort of a whole bunch of different allocations that use as little of the cache as possible. And then somehow we're going to stitch or pack these solutions back together again. And that's the online parallel paging problem. Okay. There are also reductions between green paging and parallel paging. So we've got a theorem that if you have an upper bound for green paging, then we also have an upper bound for parallel paging. And if you have a lower bound for green paging, then you've got a lower bound for parallel paging. And moreover, if you have a green paging algorithm with a competitive ratio, say theta beta, then you have an online parallel paging algorithm with a competitive ratio that's also theta beta. And again, all these, there's a constant factor of resource augmentation, just as in standard sequential parallel paging. So these problems are really they're distinct, but they're closely allied. And thinking about green paging is the right way to think about parallel paging. Okay. In terms of a bound for green paging, no deterministic online green paging algorithm where you've got a maximum cache size of k that we can have and a minimum cache size of k over p can be log p competitive. And so, right, so basically we're gonna, people can ask me afterwards at this time where these parameters come from, but basically you've got a maximum cache size of k, minimum cache size k over p, and you can't do better than log p competitive. And what this also means is that no parallel paging algorithm can be better than log p competitive, where in here, p is the number of processors. So no parallel paging algorithm can be better than log of the number of processors times optimal in the worst case. And there also exists a universal green paging solution that is log p competitive for all request sequences. And I'll explain a little bit more what I mean by universal, which is that there is one strategy for partitioning the cache among the threads that is optimal. And if there's time, I'll show you a picture of what the strategy looks like. So there is a universal strategy that we can use that gives us log p competitiveness, so log p times optimal, and that's the best that we can hope for. Okay, so that's the bounds for green paging and parallel paging. Okay, and basically what this means is that we have a universal log p competitive parallel paging algorithm. Okay, so I'm not going to go into this in great detail, but I want to give you a sense about what this universal solution looks like. So the universal solution is a repeated post-order traversal of this tree. And let me explain what this tree is. Actually, maybe I'll do this in the other way around. This picture on the bottom is what a universal solution looks like. And the first thing to note is that we can make the universal solution just out of boxes. So we're not even going to worry about like smoothing out curves. We're just going to have boxes. And it's kind of a fractally looking solution where most of the time in the green paging solution, you have very small boxes and we're not using very much memory. And then every so often you have a bigger box. And then every so often you have an even bigger box. And so it's sort of a fractally way of assigning memory to the different processes. And the way to come up with this fractally type solution is to take this tree with a big box as the root and smaller boxes, the children, and smaller boxes, and just sort of traverse over this tree over and over and over again. And what I think is amazing is that this gives us the optimal solution to the green paging problem. So just one solution, one way of assigning these boxes that is optimal for all algorithms. And yeah, I will say that when we realized that this was the case, this is completely not what I believe could be possible. I think I'm going to skip a little bit over this analysis because I'm hoping that we've got time at the end for some questions and for some discussion. And so I want to end a little bit early so that there is time for it. So what I didn't say in this picture here, because I didn't have time, or apparently I did have time, but I didn't think I would have time, is that once you have this universal solution for the green paging problem, then what you need to do is figure out how to stitch all of these solutions together. And you can do this with a kind of online box packing problem, where every so often you turn on some of the processors and turn off others, and basically pack a whole bunch of these solutions together. That's how you stitch them using an online packing algorithm, so that then you've got a bunch of separate green paging algorithms that you turn into one parallel paging algorithm. And what I find exciting about this problem is I don't actually know whether this universal solution is a positive result or a negative result. So the optimist would say, hey, we've got this really exciting positive result where we've got one universal solution that we can use to solve all green paging problems and all parallel paging algorithms. And the pessimist says, no, this is actually a negative result, not a positive result. And the optimist says, but look, we've got tight competitive ratios for both green paging and parallel paging. Like, we can't do better than log p, and we have a universal solution that achieves it for all. We've got a universal competitive algorithm that is optimal competitive ratio on all inputs. The pessimist says, yeah, that's true. But the pessimist says, well, this is still a negative result because the algorithm is not smart. Like the algorithm is doing the same thing without reading the sequence. It's just one solution for everything. The optimist says, yeah, but universal solutions are good. And the pessimist says, but not all solutions have the same requirements. A good solution should be tailored to the problem instance, and we provably cannot. And the optimist says, all right, yeah, but even so, we're much better than natural and naive solutions. And the reason why I'm talking about sort of the optimist versus the pessimist is this also explains why I'm so excited about sort of pushing forward on this problem, as well as talking to people who've got very different backgrounds and insights, is on one hand, we really now have a sense of how to think about parallel paging, where we really want to think about from the perspective of each individual thread. Each individual thread should solve a green paging problem and consume as little of this shared resource as possible. On the other hand, I think in instances that are not fully worst case, such as the stochastic instances that one of the listeners asked, as soon as we've got some stochastic instances or something that is not fully worst case, then we can tailor the green paging solution to the specific instances. And I'm excited to think about how to do that. Okay. I think, so this is a slide saying a little bit more of what I just said, which is it's time for some beyond worst case analysis. So learning augmented algorithms, other sorts of models, stochastic inputs, and also to see what happens on traces in actual systems. And so so far I've been working on this with colleagues and students, and it's just a really exciting problem. So I think what I want to do is end a little early because I'm hoping that it's possible to turn on mics and have a little bit of discussion. But let me just end by asking if anybody knows, who hasn't seen this slide before, knows what it is and also what the context is in my talk. And of course, nobody can answer, so I'm just going to give the answer myself, which is this is my summary slide. So when I was teaching first in COVID, I was teaching a really wonderful class of honors students during COVID, and I told them whenever I say a dumb joke to unmute the microphone, laugh, and then mute it again. But I think that doesn't happen here. So let me just summarize where this talk came from. And they would do it. So first I had a wonderful experience with COVID where every time I said something silly, students would unmute and laugh and mute again. So we now have the tools for reasoning about parallel paging. So we need to think about green paging, this notion of cache impact. We understand, a lot of the packing issues. And now we need to use these tools for beyond worst case analysis. And we also need to understand how this affects the performance in actual systems. So I'm going to conclude here, and I'm really curious to, to field any questions and talk more offline if people want to pursue it. Thanks a lot.
Yes, thank you. First, let me say thank you for a great talk, and this is echoed in the Q&A by some of the participants. We also have a question from Xiaodong, and I would like to invite them to ask their question live. So I've clicked the button, which should allow you to ask your own question if you would like to.
Okay, can you hear me?
Yes.
Oh, hello, Michael. A great talk. Good to see you again.
Yes.
Xiaodong Zhang from Ohio State.
Sure.
This is also my research area. So my question is, you talk a lot about LRU, but in LRU,
Yes.
the replacement decision is really regulated by a deep LRU stack. We all know that. That only has
Yes,
one
exactly.
exit gate, right? You go the bottom of the stack. So if I'm a cache block, the only access for once, I stay in that stack for a long, long time. I don't belong to the cache. So for example, one time or few time accessing once, and then you gave the, I think the Targent's LRUK less equal to optimal K, K divided by 2. I think that's very average. For one-time access in production system, there are a lot of one-time access. In fact, when I was in graduate school in Boulder, Colorado, and there's a research center called NCAR, National Atomistic Research Center. Lots of climate scientists access their data center. 50% of the scientists access the cache one time. Okay, so lots of one-time access time. LRU is really doesn't work. And then so cache they don't belong here. They really violate your green principle. And so I assume you look into the LERS algorithm, which was 20 years ago. My student and I developed. Has been widely adopted in industry, and this really addressed the LRU limits. But the advantage to retain the LRU big O1 complexity. So and you also cite the paper 1971, 1972 IBM journal, and then they defined the reuse distance for that.
Yes,
they defined the reuse distance. The LERS algorithm used the reuse distance, use 2 stack so that which block will be replaced. It's not by recency of LRU, but by the recency of that. And so my question is, how do you compare LRU and the LERS in your algorithmic perspective, since this algorithm has been well received by industry? Here's my question.
So that's a great question. So one of the things that I'm sort of proud of about this work is that it completely separates things that we thought could not be separated. So one of the things that it separates is the exact replacement policy, as well as the how do you divide the cache, as well as the even when we're thinking, I'm going to come back and answer your question directly, but and even when we're thinking about, in parallel paging, there's this really complicated interaction between the different processes. And what we showed is that we can actually think about the processes separately by viewing it as this problem of green paging. And then separately, we can think about the problem of replacement policy. And so you're right that, LRU has got a great theorem, which is like it's too competitive with 2 resource augmentation. But it's also the case that that for some workloads, LRU is not as good as something else when we really want to optimize the constants, and usually we do. And so this framework says that one of the right things to do is actually think about the replacement policy in the context of green paging, one processor at a time. And this will also translate and say something interesting about parallel paging. And so now we can think, all of these separate issues that seem so completely entangled a priori, we can separate. And, again, I guess I think it was exciting to me that LRU also works well, even when the size of cache changes over time. And it's likely that various algorithms, whether it's the clock algorithm, which is frequently used in operating systems, or some more specialized solutions, also work well. And And it's also nice to think about cache hit curves when you're trying to compute the whole cache hit curve, you know, with various, like all of these things that we're thinking about, we can now think about in the context of parallel paging.